Hello, and thank you for joining me. You're here on this guided project with Data Science Teacher Brandon, and we're going to be building a TensorFlow model, a classification problem. Okay? So this is a fairly easy data set, and this is really just to practice getting started with TensorFlow on a spreadsheet type of data set. Okay, so I really would say spreadsheets, computer vision, and NLP, they all have their different kind of flavors to working with the data and then building the model. So here on a spreadsheet data set, we're going to do a comparison between machine learning models and our TensorFlow model. I really always find that the best way is to set the baseline as your machine learning model and then really try and beat that. You should usually be able to beat it. You can't always, but you can usually beat it with a deep learning model by a few percent or a very large margin sometimes. Okay? So let's get started. Okay? So first thing we're going to do is importing our libraries. So importing pandas, numpy, SNS, and pyplot. Good just to do these. Almost always need them once or twice. It's good just to import all of your data science type workbooks. And here we're going to do import TensorFlow as TF. Okay. We're going to work with sklearn a little bit to do a little bit of the pre-processing and a little bit of the and for our models as well. So what we're going to do here, we're going to import standard scalar from sklearn.preprocessing, and from sklearn.composition, we're going to import PCAs. Okay. And then we're also going to use sklearn's train split in our model, our train by split model, part of our modeling section today. Okay, and from our two models, we'll use random forest, which is just, it is generally a pretty good model. It's very popular, but it is actually a good model for a good reason. And it works well. It was popular because it is a good model. Okay? And I always like to, it does have one set of mathematics, so I think it's always good to try another good model, gradient boosting, that uses a similar concept but approaches it with a different set of mathematics, and you can get different answers. Sometimes better, sometimes worse. So good to try, really try random forest and gradient boosting on most of my workflows and see which one is the best. Okay, so we'll run that and we'll do that. I have the data set on my reservoir today, so you'll be able to download it directly. You won't have to download the data set. Or we'll be able to download it directly from my reservoir using pandas. Pandas is awesome. Okay, so we'll go that. I'm loading the data set. And not import gradient boosting last gradients because you need to spell things correctly. That happens. Sometimes it's good just to see and get an error and make sure you spell things correctly. But it is obviously good to try and spell it correctly the first time, but sometimes we're human, right? So errors are not the end of the world, right? Well, hopefully. So here we're going to import the data set from my reservoir using pandas, and then we're just going to take it. So this is a pretty standard data set. We're going to be predicting if they leave or not on this employment prediction, whether or not they will stay or leave the company. So again, just do really easy workflow from Kaggle to get us practicing building a machine learning, deep learning type of workflow, how we go about doing that, and why we go about doing that. Okay? So here we're going to do, I like to have a little bit of fun, so nothing really super fancy here. I just made a palette of colors. You can go to colormine.io, make your own. And I just made a little color palette. I get kind of bored of the standard colors, so I have a little function that I've made that just randomly selects. Basically what this is doing is, if you don't give it a seed, it's going to randomly select from this palette. So sometimes you get some repeating colors, which look a little bit weird, but sometimes you get kind of new mixes and stuff. It's a little bit fun. Okay, so just doing that just to have a little bit of fun today with our color palette. Standard C1 palette. Okay. So here we're going to do still just like you would for machine learning. We want to do our basic. We want to do our inspection of the data, especially for spreadsheet type data. There's a lot of pre-processing we can do, almost more than in other times, other sets, more variations at least. And so we just want to make sure that we inspect our data and see what we can do. There's a lot of opportunities to become all better. So we're going to go 4 feet in df columns, and that's giving us a list of all the columns. We're going to if feet, if the data type is an object, we're going to go value counts, the df feet value counts. Yes. And then what we'll do is then plot that value count. It's going to give us a count of each time the index, or sorry, the value count, and the category is then index. Plot this and get a nice little kind of our font that's dimensional. Okay, so we're going to go else if the feature, well, if it wasn't an object, you know, in this data set there's only numeric and float. So really, if it's not an object, we're going to go plot the histogram. So we're just going to plot it. We'll have to do value counts first, and we're going to go kind equals hist. So now we get the hist form. And we're setting the title in both of these to the feet, and then our random color. And here I'm just selecting, if you put in random color as 1, it will return 1 color. And then we're going to show, make sure we print the plot, show it, so that when it prints, or on every iteration, it prints it out so that it's just not all on top of each other. And we get funky colors. And just having a little bit of fun here, just going, mixing it up a little bit so it's not always the same. And here I write my observations, what we do see and do not see, what the opportunities are for pre-processing. Pretty standard machine learning workflow, just, you know, on a regular spreadsheet type of data. You want to write what you're going to be doing on your pre-processing step before you go into your machine learning. Okay. So then we're going to look at that again, but look at it in context of our target. Let's see if we can notice anything a little bit different. So we're going to do the same thing for feet in df columns. Df feet, and if that data type is an object, we'll and then the thing we're going to do differently here is going to be hue is equal to the target, and notice that here x as well as equal to our feet. It's going to transfer this all correct. So df feet equals object, SNS count, x equals feet, hue equals either or not. And then in the next one, just like we did up above, if it's not an object, then it's going to be a numeric column, and so we can plot a history. We'll do the same thing here. X equals feet, hue equals our target variable. So we're expecting everything in our target, and this can be kind of good just to understand what it is. Here we're also going to change, we're going to add the title, and we're going to add the title is going to be feet. And we're going to set font size to 22 and font weight to 8. And different colors than I originally did because it's random. So you can't say this is printing out the seed. If you wanted to put that same number in, you get the same color split. Okay, so it really depends what you're looking for. And again, it's just to have really no reason to do that, but to have fun. Okay, and then write down my observations. How it relates to the target. This might help with the pre-processing each feature, right? So understanding the distribution, but then understanding how it relates to each target. Okay. So just going to check for null values, and this was, again, a pretty easy data set, so there are not going to be any null values. We run df is null dot sum, and we get here it sums up the total true values, the total true values in each column, which is none, so there were no null values. Okay. All right, so then we're just going to get this ready for bucketizing. So this was a little bit. This is just a little bit too much to work with. I put this into smaller amounts for one-hot encoding later. So we're going to do a histogram in C1, and we're going to look at this. So I'm just going to then combine a few of the, this is fairly easy, maybe not the most common way that you would do this, but I was just going to, it worked. It was a little bit easier to do just on this specific type of data set. So it was just a really easy way to do this. So here I'm just going to replace 2012 with 2013, 2014 with 2015. So getting rid of every kind of other number, just reducing the numbers so that if we were to one-hot encode this, we would now only create 4 different categories, 4 different columns versus the other way where we'd have it's 7. So we're going to reducing it a little bit. We're going to then one-hot encode. So we're going to do get underscore dummies. And we're going to, I did the columns here first just to get the list of the columns. and then okay. And then now we have our data set with all of our features. Okay. So heading into the train, or sort of modeling section. So first train test split is usually the first stop here. And so what we want to do is df dot. Now this is a personal kind of style. Sometimes people don't like to write the list of the columns. I like to have access. This is I often want to experiment with, say, not having one of these columns go into one of these features go into my modeling section and just see really maybe I should be getting rid of some of these. I probably don't truly problem. Some of them are probably pretty useless, so it will probably help our model to get rid of some. So this just allows your workflow, allows experimentation in your workflow to have this access to these features as you're heading into the modeling section. So we're going to build a list of the features and then a target, so a target, which is one here. We might have more than one target in the future, so okay, so we have our features. We're going to build X, and so df features is equal to X, and then Y is equal to df. And these two sides. Okay. Now we're going to do a train test split. So I have a short form way of running a train test split just because you always have to change train and test so much. So it's a lot easier if it's only one character that you have to change. It truthfully will save you at least 10 minutes every workflow just doing it TR and TS instead of train and test. And I think it's pretty, it has a good short form for writing variables. It's just getting rid of vowels. Usually it's still pretty understandable what that word is without just the constants. Okay. So if we run this right here, and we have our train test split done. Okay. And we're putting the x and the y into that we just did above. So here we're going to go standard scalar, and we're going to hit this standard scalar with our x, just our x's, and then it's going to go into our standard scalar. We're going to assign that to our standard scalar. Now that it's ready, we're going to transform. We did that first. We just fitted on the x so that we could transform both the x and the the train and the test with the same function with the standard scalar. Okay, so transforming both of those. And then we're going to head into doing the PCAs, getting the principal components. But Sklearn is amazing because everything is very similar on how you use different functions and stuff. So we're going to go PCA. So PCA lowercase is equal to PCA bigger uppercase. We're going to fit that just like we did up above, and then we'll go PCA dot transform, and then PCA transform. Just run those two cells. Okay. We're going to build a little function, very simple function, just to get our sklearn scores so that we can have it. Little mistake. Gotta make sure that you still spell it. You know, it's only one character, you still have to spell it. Okay. So here we're going to go df get scores. We're going to give this function a model, sklearn model specifically, and we're going to then fit that model.fit. We're going to train it on our x and y. We're then going to go model.score. The training values, and then we're going to do a model. Test scores. Okay, so we're going to assign that to train and test, score train, score test, and then we're going to return both of those. Then when we do our next section, it will be very easy to collect these scores, and then we'll be able to do a comparison down below at the bottom. Okay, so first thing we're going to do is initialize our random forest classifier. And then we're going to go get, we're going to assign that to RF, and then we're going to go get underscore scores, and we're going to pass that RF, our new model. It's going to return then our two scores. And so we got an 84. Let's see this one here. We're going to do gradient boosting now. So gradient boosting classifier. Run this. Let's get another score. We get our best score for today, 87. So this is what I'm going to try and use. I was just gonna surprise but I'm not going to be able to beat this, or I'm going to get very, very close. This is no substantial, but sometimes there's just an ultimate limit to what you can do with the data to predict your target. From here, you'd be looking at collecting new data. But this is a good way and good understanding. Usually, this is my benchmark now. I want to make 87 my goal. I really feel that almost all the time you can beat it. Sometimes, again, there's just a limit on what you can do. Sometimes machine learning gets to that limit. It doesn't always, though. Deep learning will very often get to the limit of what the data can do in terms of predicting. So there really just is only so much it can do. There's no magic here, right? So we're also going to then import logistic regression CV and explore as well. So we got pretty good scores overall. Really nothing, everything above the 80s was quite good, especially for really just using the default without doing anything else. And this is really what I did. I didn't do anything specific with hyperparameter tuning. I just put the model in and the defaults work pretty well, truthfully. And so really this is just to set the baseline. So we didn't spend a lot of time on the machine learning. Although if we were just building this as a principal model, we could spend more time. Anyway, so moving on to this one. So we're going to do our build one model. So we're going to make a function so that we can allow for experimenting and trying to, again, beat our baseline score. Okay. So we'll go through this. So what I'm going to do first is in the first section, I'm passing it the recurrent layers. I'm doing a a backslash to make this continue on the same line. And then I'm going to do the first dense layer that we have, and then the first group of dense layers, and then the second group of dense layers. And then I'm going to do loss, and we're going to do TF cares losses. And then here what we're going to do is we're going to go sparse categorical cross entropy. So this is just to highlight, we're giving this one column, and this is sparse. It seems counterintuitive because usually a sparse is lots of ones and zeros. In this sense, when we're using our loss, we're going to put sparse when we're giving it one column or two different categories, or all of our different categories are all in one column. It's not a one-hot encoded vector. Okay, so this is something to be aware of. If it's a one-hot encoded vector already, it would be a categorical cross entry. Okay? And we'll come how to do that in future classes. Okay, so then we're going to go for the optimizer. We're going to set it optimizer tf.cares.optimizers.atom. And atom is just tricky. It's a good, at least you're the first time getting started. It's a good starting optimizer. Usually works fairly well. There could be better ones, but it's a good starting point. We'll initialize our model. So tf.cares.models. And we're going to do this sequential. We're going to add, so if this is a sRNN, so if it's an sRNN, we'll add in our TF cares simple RN and activation is going to be the current act, rec act, which is 10. Okay. And then our input shape is going to be our X train, so the number of features is going to be organic then with selecting in and out different features. And one, you just have to let them know that there's a depth, there's only one stretch, because recurrent layers are used for other things which have many dimensions, kind of like if you think of a picture, red, blue, green. So there's 3 in the Z dimension, there's 3, so you need to often specify this for more advanced layers. Okay? So we're going to, so if it's an SNS, if we give it the SNS argument, then it's going to be sRNN. We're going to then give it simple RNN. If it's not that, then what we're going to do is we're going to go model.add, and then we're going to do an LSTF. Okay? And we're going to set the activation to be the same. Okay? And then doing the input shape as well again, because this is going to be our first layer, one or the other type. Okay, so we're going to add either one of those. Then what we're going to do is for underscore in np.range, we're going to do number of dense layers. So we have set it to 1 here. And then we're going to go model dot add. We're going to add tia dot case dot layers dot capital D dense and activation. So ran all of these. So here in the next one, then what we're going to do is tia dot, or sorry, we're going to go for underscore apply dot arrange np dot arrange. So there's no real activation. And we also make sure we add model dot. So we're going to have two sections. This will allow us to, often when I find more dense layers by itself doesn't really matter, but often what happens is having one or two of different widths, so different number of neurons can really just, I don't know specifically, it's hard to really think through exactly what it's actually finding when it does that, but it really find one wider one and one smaller one, or one smaller one and one wider one, and often actually be the secret in getting a model better. Okay, so this is just going to add how many ever number of layers we want to. It's going to add two sets of this so that we can control kind of different styles and just different widths of those. We're then going to add, so model.add, we'll go doing our output layer, we're going to do tia.cares. And this is our output, so we have two classes, and this is going to be, it's going to come out in the form of a one-hot encoded vector that has one for each one column, for each one feature, for each class that we had. So this is going to be use then the softmax prediction for those. Okay. So then we're going to go model.add, we're going to go loss equals ls, which is the sparse categorical cross entropy loss right here. Okay, our optimizer is going to be the atom optimizer that we set up above. And then what we're going to do is metrics equals accuracy. We're going to return model. Okay, so this is going to build our model. All this is going to do is set up the, okay. So now we have our model. So to explain what I did for the experiments, the reason that we put this into a model was to experiment. And it takes a lot of time to do this specifically. So you don't want to, you really want to have a good reason you're going to be using it deeper. Hopefully because you need to get a better score, but sometimes you might not be able to. So really, I went through a lot of work to get my deep learning model working just as well as my machine learning model. If you can make it working better, but really, if you think about the extra 3 or 4 days it took of experiments to get it working as well, you always have to ask yourself, is it worthwhile? So deep learning is a bigger commitment, and really this is where it is the big commitment. Time in training, but time in experimenting with the architecture as well. It's not something you generally know going into building a model. What is the absolute best architecture? Okay. So here what I've done is set up experiments, epochs, learning rates, recurrent, a list of the recurrent layers, the number of neurons, and the number of activations. And just in the loop, I would experiment with these, and I'd be calling them in the model factory function. I find a good one, and I make the change up here at the top here, and we have our distance set up right now. Okay. So I go through and do that. Okay. Go through and doing all of that, and here doing it on an individual basis, we'll do it together. So we'll do build, or sorry, model underscore factory, and we're going to be returning this model. We're going to have a model from that, which we're not going to set our defaults. We use those as placeholders to remember exactly what model, what architecture we're finding is good as we're going through each experiment. And as we've done that, we're going to go model.fit. Train X train, Y train, then we're going to get the validation data is the X in a tuple is x test, x, y test. We're going to go bash, which is size is equal to 8, and epochs is equal to 150. Okay? So history dot history. Okay, this is what I've assigned from our model dot fit. This is the history of our epochs. We're going to go. The easiest way is to put this into pandas and then do pandas dot plot. So you now have a data frame. Plot that. You give it a title of history of model. Okay, we'll show that. Then what we're going to do is model dot eval u8 and model dot evaluate for a train and a test sets. Okay, so we'll run those, and we'll run this right now just so that we can, so I can show you the next steps. This could take a little while to train. And here what I've done is I put all of our training scores and our test scores down to the bottom. I put our neural networks down below. Or sorry, put the names of the models. I'm going to put the scores into a list. So this will become our column title. This will become the data in our column, column title, data in our column. I'll put that into the pandas. And here I'm just going to say the index is equal to the model names. And I'll sort by the test score. Okay. Now, you'll find, really just even looking here, we can see that the .73, and I got 0.74 on the gradient boosting. So there is just, it's a good way to confirm that really you have got to the limit of what you're going to be able to do with the data set. You will often find 99 times out of 100, you'll be able to do it at least a little bit better, maybe only by a few points. But you usually end up being able to do a little bit better. There's one thing to be conscious of is it took me a lot of time to find this. It was not something that I did right away. It took a while. So it's really one of those reasons you need the reason to go for the extra score, to really be putting the extra effort into the deep learning model, because it does work better, but there is a time cost in building it. Okay? So thank you very much for joining me today, and I will see you next time.